Hello, this is Kevin Buzzard talking about solutions to sheet 1 of section 7 topology of my Formalising Mathematics 2022 course. At topology, you sometimes get infinite unions of open sets, and so we have to learn how to do infinite unions, and of course you sometimes get infinite intersections of closed sets. So there it is. That's how we do it. We have this there slash capital U or slash union with the capital U is a union over the idea is A is a function from iota to the subsets of X. So iota is the indexing type, and so A is a collection of subsets of X indexed by iota. So we're not doing any topology right now. There's no topology on X. X is just an abstract type, and there's how to do infinite unions. And the thing you need to know is for the one key thing you need to know is set.mem union. So set.mem union says an element is in the infinite union if and only if there's an I, if and only if it's in one of the pieces. There exists an I in the index set such that it's in the corresponding set. And similarly there's set.mem inter with a capital I for intersection. And you can take unions over more than one thing at once. You can take unions over propositions, which is quite funny. I talked about that in class. I'll probably write something about that in the course notes. But let's see. Oh, there we go. There's set.mem inter. You're in the intersection of a whole bunch of sets, if and only if you're in all of them. So let's see if we can do some of these questions. This says. What does this say? We've got a bunch of sets, capital Fi, and so they're all subsets of X, and we've got a function from X to Y. And so we take the union of all these sets, and then we take the image of that function. This is the image of a set under a function, the push forward. So I claim that the push forward of the unions, the image of the unions, is the union of the images. So that's not so difficult to do. So I guess. We could do it from first principles. It's interesting to see what it's called. So there we go. That's sort of interesting. So there's a one-line proof using a result in Lean's maths library. Set.image union. Note the capital U because it's a union. Union with a small u means union of two things. Union with a capital U means arbitrary union. So we're claiming that the image of the union is equal to the union of the images. So what does Lean call that? So it's in the set namespace because we're talking about sets. So it's set.image union. You start reading from the beginning, and when you feel you've said enough, you stop. So that's how that proof would work. But I mean, are there any just finish to it? No, hard luck. So let's try x, y, and now let's try finish. No, hard luck. I'll try tidy. I just try. Sort of interesting to. Oh, there we go. So, tidy just follows its nose. We can see what proof tidy came up with. So there we go. So there's an example of a proof. So it simplifies everything, and then it does split. And then it does an intros and a cases and an induction. That induction will just be a cases anyway. And more splits and assumption and referral, intros, cases. See, what's this induction? Oh yeah, okay. I think probably cases would work as well. Split. You see, all it does is completely basic tactics, and you just follow. The computer's written that proof. Yeah, I mean that's longer than the proof we'd come up with. But there's an example of how one would do it. Maybe because this is the first one, maybe I should do it by hand. So I'm going to do it with split first. Because it's an if and only if, so we've got to prove inclusions in both directions. And now, y is in the image of... so y is in the image of something. That is an exist statement. I mean, if you like, so we could do intro H. Look at this, I'll do it super slowly. Intro H, y is in the image of something, so I can rewrite set.mem image at H. you see, and you can see it's an exist statement. There exists an x such that x is in the union, such that x is in the source thing and f of x is y. That's what it means to be in the image of this thing here, right? There exists an x in the thing such that f of x is y. But I think that that's definitional. So now I want to do cases h, right? I want to do cases h with x, hx. You see, this is exactly what tidy was doing. It was just trying stuff like this. And you see, if I delete this, yeah, see that rewrites definitional. So we could do all this. We don't have to do intro and then cases. We can just do rintro. We don't need to call it h. We can just put x hx here, and that will do intro and the cases all in one go. But you see, you can take hx apart as well. Hx is an and, right? You see, there's an and somewhere, and if I hover over the and, then everything lights up, which means that this is, you know, something and something else, right? And so we can keep splitting. We can go, you know, we can go crunch, hx1, hx2, right? There, and then you see we've got these two hypotheses. But next, you don't need to. These pointy brackets are right associative, so you don't need those pointy brackets there. They associate to the right. And also, little y is just an arbitrary element of capital Y. We don't know anything about it. Right? The only thing that little y does is it sits there being an arbitrary element of capital Y, and we know that it's f of x. And we're trying to prove that y is in something. So clearly, the way we're going to do that is we're going to rewrite hx. We're going to change that y to f of x, right? That's the only thing. That's the only thing we know about y, is that it's f of x. So ultimately, that y needs to be changed to an f of x. Yeah, we know that x is in this union. We're trying to prove that f of x is in the union of the images. And so we can do that by just changing h. We can just put refl here, and now you see the goal. There's no y at all anymore, and the goal is f of x here. So we've defined y to be f of x. That's a little hack, right? That's the refl. The R case is refl hack. And hx1, you see, we could also keep doing the same thing, right? hx1, I mean, maybe I'll go easy on you. Now we've got a hypothesis that x is in the union, and we're trying to prove that something's in the union. So we could rewrite set.mem capital union at start. Let's just rewrite it everywhere. So now you see that says there exists an I such that x is in f of I, and I'm trying to prove that there exists an I such that f of x is in f of fi. And so clearly the same I will work, right? So we can do cases hx1 with an I, well, let's call it j, hj, and then we can use j. And now we've got to prove that f of x. You see, this doesn't exist, right? If you're in the image of something, the claim is that there exists something in f of j such that f of that something is f of x, right? So this is just this is exact. I mean, it still is another u, so we could use x if you like. And now we've got to prove two things. We've got to prove x is in fj, and we've got to prove f of x is f of x. So we could split, but we don't need to split because the constructor, the pointy brackets, and is an inductive type with one constructor. To prove p and q, the only way to do it is to give a proof of p and a proof of q. And inductive types with one constructor are where the pointy brackets work. So this is exact. Pointy brackets something comma something. That should be the end of that proof. And the first something, what's the error? It says, I don't know why x is in fj. That's because we didn't write hj. So let's write hj there. And now it's complaining, I don't know why f of x is f of x. And the reason for that is ruffle. There we go. It's ruffle without the e because we're in term mode at this point. We're just writing down terms, right? Hj is a term. You know, the hj isn't a tactic. Exact is the tactic. And exact puts us back into term mode. So that's one way. And now the other way, I mean, let's just do, I mean, this, who knows what this is? This is probably an exist as well. Let's just try rintro. Let's just see if we can do this in 2 lines. Rintro x comma h. Let's try, let's guess that. And x has got type set y, so that was a lousy guess. Let's call it capital V. And now what's h? H has got type there exists a proof that V is in the range of something. So we could keep taking that apart, right? So that could be h1, and then we could have h2. And h2 says that y is in v, so we could call that hyv. That would be a sensible name for it. Now what's this h1? h1 says v is in the range of something. So again, that's an exists, right? So we can go here, right? So let's call it x and h again. Now let's see what they were. X is in iota, so a better name for that is j. We could call this hj. And hj says lambda r. We could that I'm going to simplify it in my head, right? This is a function, it's a lambda, but then we're evaluating that lambda at j, so we just let I be j. So it says the image of f of j is v. The image of f of j is v. I wonder if we can get, can we just do REFL? I wonder if we can do REFL. Yeah, we can, great. And now there's no v, you see, it's defined v to be, f of j. And now hyv says that y is in the image of f of j, and I've got to prove that y is in the image of the union, so this is exact. So again, it's an image, so the image of, so I've got to give an element of the union, and that is going to be, I see, we need to take this apart. We need to keep taking hyv apart. Y is in the image of f of j, and that is an exist statement. So we can go, so there's going to be an x here, x hx there, and now hx says x is in f of j and f of x is y. So we can probably put ruffle there, and now we've got no y. And now we've got to prove that f of x is in f of this thing here. So this is exact x comma something. And what's that something? It's two things, so we could do underscore underscore. The second one is REFL, and now what's left? We've got to prove that x is in the union of the fi, and so that will probably involve saying it's j or something. Is it? No, j has got to. So we want to set x, so it's going to be f of j, because that's the only thing it can be. And now I've got to prove. I've got to give a proof now that f of j is in the range of this function that says I to f of I, so that will be j comma something. No, I've lost it. Is it pointy brackets? Something comma something. Let's try that. So what does it want here? It wants a proof. Oh, I see. It wanted this one here. It wants a proof that f of j is in that range. So maybe that's the place. Oh wait, can I just do this? That looks good. And now here I can put j comma something. And now here it wants a proof that f of j is f of j, so that's ruffle. And here it wants a proof that x is an f of j, and that's hx. There. So you can see how tidy is doing this kind of goal. Because all you're ever doing is you're saying, well, there's a v and a j and an x and an hx, and then you sort of rearrange everything in the where it can go. Right. So that was called set dot. What was it called? Image union, and now this is pre-image. So this is exact set dot pre-image union, right? Pre-image capital union. There we go. That's done that one. And this one is exact set dot pre-image inter. No, with a capital I perhaps. Yeah, I want to do this one though because we haven't done pre-images and we haven't done inter. So let's do x this time. What have we got here? And then I'm going to split it. And let's just. And now let's. This says x is in the pre-image of something, so it says f of x is in the intersection, and so I think it might say for all. I think this might say for all something, intro h, and now this is x is in the intersection. Can I keep it? Can I keep introing? Yeah, I can. And now I've got to prove that I is in. Oh, that's hi. Oh, I is a lousy name. This is v, hv. What's h? H is a hypothesis. So we're going to feed stuff into that hypothesis, I think. And hv says v is in the range of something. So that's an exists, right? It exists a j such that v is equal to the preimage of g of j. So I can pull that out with this j, hj. No, but now I've got to use rintros. So hj says that v is that, and so probably I can change that with ruffle. Yes, I can. Right, and now h says f of x is in the intersection, so it says, so I can specialize. I can specialize hi. I would have thought. Oh, hj. I can't. Oh, it needs a set y. Have I got a set y? Ah, let's try g of j. There. And now I've got to prove that g of j is in the range of something. So that's going to be pointy. It's going to be something like that. And now it wants an iota. So that's going to be j. And now it wants a proof of that. And that's going to be ruffle. And now I wonder whether that's exact. Is that exact h? Yeah, it is. So it's exact this. There we go. So that's the proof of that. And the other way should be similar sort of. Well, now we can kind of look at what we've done. Or maybe we can't. So intros h, and then there's an I. Is this still this? I'm going to go rintro again. Rintro h I. I is in the range of something, so that was. Have we seen that before? How can I do pointers? X, y. What are x and y? X is in iota, so that's a j. Oh, so what's this I? I've got this I wrong again. It's a v. And now what's little y is almost is a random thing, so that should be a ruffle. And now we've got to do, so it's exact h underscore 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 underscore. No, okay. Let's stop. What have we got to feed this thing? Let's try feeding it j. It wants a set x. Set x. It wants. I suppose it's going to want f inverse of gj, right? Because that's the only thing. Oh, it doesn't like it. Ah, bingo. So, and now I can start maybe putting. Ah, wonderful. Now it says I can't prove that f inverse of gj is in the range of this, and so I'm going to put pointy brackets, something comma something, and now it wants an element of iota, which is going to have to be j, and now it wants a proof that f inverse of j is f inverse of gj, so it wants a ruffle, and there we go. So there's a rather nice short proof of that. So that was image union, and that's pre-image union, and that's pre-image inter, and so obviously we're missing set.image inter. So check set.image inter, and there you go. It's unknown identifier, which means that there isn't a theorem called set.image inter. So that either means it's missing from the library, or it means it's not true. So is it true that try and prove it? Is it true that the image of the intersection of a bunch of sets is the intersection of the images? Is that true? So there we go. And now what's all this? The union of the AI is a subset of S, if and only for all AI is a subset of S. Yeah, that sounds true, doesn't it? It's not REFL, is it? No, hard luck. I guess it wouldn't be. Yeah, finished does it really quickly. Oh, this should be a. Does finish do all of these things? Oh, finish doesn't do that one. Does tidy do it? Yeah, tidy does that one. And now bounded unions. I'm kind of rather regret doing these in some sense, because I've realised now that somehow this is the union for I and S of AI, and somehow this union for I and S means the union over all I such that I is in S. So it's a union over I, and then it's a union over proofs that I is in S. So if you're brave, you can use set.mem union, but because this is somehow a special case, the union over I with the property that I is in S, and they made some this bounded union lemma here. So there's that, and now. And similarly, set mem binter if. Let's see if we can do some of these problems. This will be called set.image binter. Exact set.image binter. Oh, that's interesting. Set.image binter subset. Oh, sorry, I'm not doing because I'm talking nonsense because they're unions. I bet it's called that, yeah. Aha. Oh yeah, set.image binter is exactly, that was the thing that was missing up here, right? We didn't have set.image inter. Am I right? Where was that? Yes. Set.image inter is missing, and so is set.image binter. And now what does this say? The preimage of the intersection is the intersection of the preimages. But under this funny, I mean, maybe I'll do one. So x, so split, and now I've got to figure out, so this is going to be rintro h, and that is probably a for all statement, and so this is probably a for all statement, so I can probably keep going. So I'll put x, I've got an x already, let's put a. A has got type set x, so why don't I call that u? And then u is in the range of that, so that's hu. U is in the range of that, and now I've got to prove. Oh, after split, I should do this really. I don't like having two goals when I'm only working on one goal. And so can we do better? Yeah, u is in the range of something. That's an exists, so I can probably do this. A, B, let's see what A and B are. A is in iota, so let's call it J. And B says something equals U, so that's probably ruffle. There, and that means actually we don't need to name U, we could just do that. And now I've got to prove, so now this is going to be exact H, I don't know, what's this, what do we want? Oh, J. I don't know what to feed H. Oh, it wants an element of set Y. What have we got? We've only got J. Oh, so it's going to be BJ. That's the only element of set Y that we can even make. Didn't still do. Oh no, it's okay. We're good. Oh no, we're not. We're not good. This is bad. It's not exact. Hey, maybe we haven't finished introing yet. Let's put that on pause. Can I keep introing? H. No, I can't keep introing. What does this want? What's the goal? Well, now the goal is an intersection. So now I can do an intro, right? Yeah. So that's a bit annoying. Okay, I'll desimplify. It wastes a line. And now I can do whatever, more intros. Intro I. I's got type set x, so let's intro. Let's call it U again, because we haven't got a U anymore. And now U is in the range of that thing there. And so that is pointy brackets A, comma B. And now we've got to do rintro. And what's A? A is a proof, so A can be H. The hypothesis is that J is in S, HJS, that's a good name for that. And B is probably ruffle, yeah, and we can get rid of the U there. And now we can start on this. Yeah, bingo, that looks good. And we're missing the proof that B of J is in the range of something. So I'll put this maybe. It wants an element of iota, and we've only got j, so it's going to have to be that. And now it wants, what does it want? Where's the error? Down here. It wants a proof that if I evaluate this function, is that REFL? Oh, curses, it's not. I wonder what it is then. Let's try this. Underscore, underscore. Oh, that hasn't worked. It wants a proof that it wants a proof that an intersection over all I in S is B. I wonder if it's H. Oh no, oh, I'm confused. I'm looking at the wrong thing. This is the problem. X is in. Oh, I've been looking at the wrong thing. HJS is a proof that J is in S, so we can feed that into this function here that wants to eat a proof that J is in S. So we do that, and then we get the statement that X is in F inverse of Bj. So this says F of X is in Bj. That's what we're trying to prove. No, that's exactly. Let's refine it. I'm confused. And now you're telling me that this proof isn't exact X. Let's desimp it again. We've finished the proof. The proof is over. The intersection over proof. What the? Oh my goodness. I'm glad I did do this one now because I'm slightly confused. I'm missing a proof that the intersection over all proofs. Can this simp know this? Simp H. This is like the kind of thing that they might teach the simplifier. Yeah, that's good. So okay, we've got out of jail, but I know so what's going on? Squeeze. I know. Set dot into true. Here we are. Set dot into true. Intersecting over a true statement. This is nonsense. I wonder if I can do this. I'm sort of quite interested in how it solved the goal. Can I do show term? I don't know exactly what this simp has done. Oh my goodness me, it's some complete messy thing. Okay, so I'm just going to put by simp HJS. I'm going to give up because that works. There we go. Somehow I couldn't quite work out how to insert the proof. So there you go. That makes me wonder that actually. So I wonder whether I was being too cheeky. Maybe I should have used this mem. Maybe I should have used mem bin to if for this one. So intro H. If I do rintro H, let's get rid of it. Let me simplify this. And now let's rewrite set.mem bin to if. There. And now I think that I will be able to. Now let's get. Yeah, this is probably much better. I think. There you go. That'll teach me. Don't mess with bounded intersections. So now I can do more intros. So that's just intros J, H, J. And now it's going to be refine H. But H has still got that horrible. So I want H to say that f of x is in something there. And now I can rewrite. So now both the goal and the hypothesis that something is in an intersection. So I can rewrite this at star there. And so now, there we go. So this is, oh, where's my tactics state just gone? Oh, have I broken? I've lost a bracket there. And now this is exact h something something, isn't it? And it wants to know the proof that J is in S, so that's HJ. Okay, so there you go. There's me thinking I was being so clever, doing intersections over proofs, but I think it might be more sensible to use the. Let's see if I've learnt my lesson. So this is intro H. Let's see if I've learnt my lesson. So H says that X is a bounded intersection, and this is change f of X is in something. See, I can't be bothered to write the whole thing, but change still does it for me. And then now rewrite set.mem bounded into star. I bounded into if at star. And now this should be easy. In fact, F inverse, do you know what? X is in F inverse BX1 is the same. This is definitionally the same as it. So I think this might be exact H. That's good, isn't it? Did that work before that? No. So that's the end of that one. What have we got left? Now set union. Yeah, let's race through these. Oh, so I found a hole in the library. Apparently this is... I wonder if this is exact set.image B union. No, it's not. Is this library set? Is this not in the library? Yeah, if anybody wants to do a pull request to mathlib, I think set.image C union is missing. I think people don't use these set unions very much. I think that's what's going on. Yeah, library search is taking a long time, which normally means it's about to fail. So hard luck. But let's try finish and tidy. Finish fails. Tidy spelled correctly. Tidy works. So there you go. Proof of that was tidy, and proof of this one is. Oh, that's interesting. We could have tried to guess. We could have tried to guess that one. That's set intersect. Yeah, so sinter subset. But then there's this because we need. It's not true without this hypothesis. So sinter subset of it. Why don't I do this one? This looks interesting. Last one. Intro X. And then HX. Intros X HX. And now I've got to prove that X is in U. So what does HX actually say? So I should rewrite set.mem sinter at HX. I'm assuming that that's there. That is there. Wonderful. So it says for all t, if t is in S, then X is in t. So now let's apply. Let's refine. Refine HX something something. Yeah, that looks good. And we're missing. Lean says I need a proof that U is in S, so it's one of the. Let's try that one. There we go. So that's a pretty short proof. And that appears to be the end of that. So that's it. Thanks a lot for watching.